Hello, my name is Ferenc Fejes from Ericsson Research Hungary, and in this talk I will show you how we implemented per packet service protection in XDP. So Linux has been found outside data centers and server rooms for quite some time now. You can find devices running Linux for industrial use cases such as automotive, manufacturing, aerospace, agriculture, you name it. And in such use cases, fast reaction times are important. And the network needs to be robust since equipment failure and link loss is more likely to occur. For example, a network failure can be very dangerous for the people and, it's also be very expensive. So the question is what we can do about it. And unfortunately not much, because as you know, anything that can go wrong will go wrong. So, but we can reduce the probability of the failure by adding extra redundancy to the system. That can be done in multiple ways, like for example using multiple physical network paths, or links, or like for example using multiple frequency bands in case of wireless connection. And vendors are doing exactly that, so they have developed the redundancy solutions and protocols. But in this talk I will not discuss them. Instead I will focus on standardized layer 2 redundancy protocol, not some vendor specific redundancy protocol. So the standardized layer 2 redundancy protocol is the IEEE.13b frame replication and elimination protocol, or FRARE for short. The standard published 6 years ago, and reliability of the network is implemented using instances of frame replication and elimination functions. Let's have an example. This is a simple network where we have 6 network switches or nodes and 3 streams. The streams in this case are just some unidirectional connections, so they are identified by their VLAN IDs and or MAC addresses. So here we have 3 streams, red, green and blue, and we have some replication and elimination functions in the network. And these functions implement the service protection for the network. Here, for example, the packets of the green stream enter the network at node 1, and here we have a replication function for this stream, and that creates replica packets and flooding them towards node 2 and node 3. And what's interesting is node 2, where the packets of the green streams will be further replicated and sent towards node 4 and node 5. And finally on node 6 there's an elimination function for the green streams and this drop the replica packets and only accept the first copy of each packet. And FRARE requires sequence numbers for the operation to identify the elimination function has already seen this packet or not. So we can't accept the same sequence number packet twice or more. So for that special, so there's a special header called redundancy tag, or RTAG for short. The redundancy tag is a layer 2 header and usually inserted after the VLAN tag, and you can have more than one redundancy tag. So for example, you can, with multiple redundancy tag, you can define redundancy domains. And this is a 6 bytes header, and the sequence number field is on the header. In the header is 16 bits long, 2 bytes. And it's all nice, except as of today Linux don't have native FRARE support. Yes, and that's unfortunate, because there are network switches out on the field with hardware support of FRARE, but you can't. The switch chip contains the FRARE implementation, the hardware, but that means we don't have a standard and portable interface to configure the FRARE, and we can't use the software FRARE either, since it's not there, not in the main line. But I found 2 FRARE proposals on the mailing list, and that unfortunately as of today none of them accepted to the main line. But if you take a look at the standard, you can see it's not that complicated. So the FRARE standard is not a very lengthy IEEE standard, and it's not really that complicated. So if you don't have to play nicely with the whole Linux bridging subsystem, the implementation becomes much more simpler. And probably that's why the proposals haven't made it to the main line yet. And luckily, XDP has all the functionality needed to implement the FRARE protocol. So, for example, you can modify the packet as you wish, such as inserting and removing headers. You can use this to handle the redundancy tag. And as you can see in this code sample, we made some space in the front of the header. Then we moved the Ethernet and VLAN headers to the front and insert the redundancy tag after the VLAN. And here's another code sample. This is similar to the actual XDP FRARE replication code. So that's implementing the replication function from the standard, but the stream identification is a bit simplified. So for example, we have a sequence number generator for the streams. That's generate the next sequence number for the packet. Then we add the redundancy tag to the packet, which was done by the previous code sample. And finally, there are we have 2 hash maps, one containing the device map indexed by the VLAN IDs of the streams, and the device map contains the interface indexes. And we use the eBPF broadcast flag to send multiple copies of the same packet on multiple interfaces. And these interfaces are essentially stored in this device map for each streams. Okay, and here's the simplified version of the elimination function. Again, we use the VLAN ID to identify the stream and look up the recovery objects. The sequence number, what we already seen, stored in this object, so that's essential. And okay, we remove the redundancy tag and read the sequence number from it and do the recovery based on the sequence number. So we made a decision to drop or pass the packet. And since we are dealing with continuously incoming packets, so we keep receiving packets on multiple interfaces. We care about the integrity of the recovery state. So we can't accept the same packet twice from some concurrency issues. So we need eBPF spin locks to protect the state of the recovery object. The recovery function here is defined by the FRARE standard, and right now is an inline function, since the eBPF verifier reject any function calls between spin lock. When we hold the spin lock, we can't make eBPF function calls, not even the built-in function calls. Okay, and so we have done some basic evaluation of the XDP FRARE. This was our setup. We have redundancy between node A and node B, and we attach the elimination program to the interfaces. The passing packets were redirected to the access port, which is ETH0 in this figure, and that was it's both nodes. and the replication program attached to the access interfaces. So what we receiving from the talker or the listener, we redirect those packets, we replicate those packets on the link A, B, and BA. And we also try to eliminate as much operating system noise as possible. So we isolated the cores for traffic generation and for processing the incoming packets with ISO CPUs and task set and such toolings. Okay, and our first test was a simple link failure test. We, under some ping traffic, we turned on one link and then turn back it on. So yeah, we turn off the one link and turn back on, and the interface, which is highlighted here with red dashed lines. We also set the link speeds to 100 megabits, and on the other link to 1 gigabits. It's just to make the switching more visible from the ping delays. And we also plotted the ping delays together with the ECMP sequence numbers. And while the figure is too small, but there were no interrupts or gaps in the ping traffic until we had one healthy path at least. So it's not really visible, but we don't lost any packets. And yeah, that's the FRERE's most most essential function, let's say. And before taking XDP, before taking the XDP FRERE measurements, we take some baseline measurements. So basically what we did is we implemented FRERE in user space with the classic AF packet API, you know, the RAW socket and AF packet. And that API is very stable, and it's here's long time, and it's part of the Linux for some time, and on an unloaded CPU, the performance of the user space FRERE is quite good. The RTT was below 200 microseconds, and that's really good. And under some CPU load, the average latencies and especially the tail latency increased. So yeah, this is the green curve on the plot. A very low-hanging tuning option is to apply real-time priority to the user space FRERE process, and it slightly reduces the average latency, but it's greatly reduced the tail latencies. And here we compare the real-time priority user space FRERE to the XDP FRERE. On the orange graph is the XDP FRERE, and as you can see, it has a lower latency than the user space FRERE, which is of course is expected behavior, and because the packet processing of the XDP FRERE happens mostly in the software interrupt context, at least without threaded NAPI, the CPU load generated by StressNG does not change its latency, but this is only true for moderate packet rates. So we repeated the measurement with 1 gigabit per second background traffic that's generated by eBPF with small with I think it's 1000 bytes packets or so, and in this case the CPU can keep up with the processing of the software interrupts, and they are deferred to threaded processing into case of the RQD. And it's just a demonstration that even with XDP we have to be careful with different execution context in the kernel, and the same applies for threaded NAPI too. We have seen very large tens of millisecond latencies on a loaded system because the NAPI threads do not have real-time priorities by default. So yeah, and so let's do a quick recap. it's possible to implement Frere in XDP, and that's what we did. Fortunately, we have stable development libraries for the job. So both eBPF and libxdp have a stable API and many headers, and yeah, it has some visible and noticeable latency advantage over the user space AF packet implementation. But we only tested it on servers or x86 server CPU, so we don't test it on low power ARM switches yet, but the latency gain may be even better on those low power ARM switches. But we do not have such measurements yet. And yeah, and it's important to note that hardware offload is different, and yeah, so if someone is looking for, say, an order magnitude lower latency, they will need Frere implemented in hardware. And that's what we said in the beginning. We don't have portable configuration interfaces like TC or so. We only have the vendor-specific tools to configure the hardware Frere. And if you want more details on the topic, and please read our paper. It's a 6-page paper with more details on the implementation and the evaluation. So that was a quick summary of that paper. And also you can contact me anytime if you have more questions. So thank you for the attention.
Clarifying question on the protocol itself. Does it try to handle reordering when you have multiple paths that are almost the same in latency, and then you can sometimes get a packet first on one link, sometimes on the other? Does it try to do anything, or does it just give you the first copy of a packet and reordering is just accepted as a side effect? Or
yes, it only gives you the first good sequence number packets in a window, and don't do any reordering. It's not defined for the layer 2 Frere. However, the packet ordering function is defined by IETF .NET that's part of the IETF layer 3 .NET RFCs. So packet ordering is a layer 3 thing in the TSN world and the TSN and .NET world.
Anybody else? Any online questions?
Yes, I see an online question here.
Yeah. Mm-hmm.
I lost it somewhere. Oh, okay. Can you use it on a single NIC system and mark packets with some different flag, like different DHCPs? I'm not sure. I think no. It's actually, you can use it on arbitrary links, and because the elimination function doesn't care about the ingress passes, so it don't know the how many copies the packet is dropped. Okay, it has a counter counting how many packets, how many replicas dropped, and one of course passed. But you can do, for example, you can send multiple copy of the packet on one pass, hoping that one of them will reach the target. So you can do that, yes.
All right. Anybody else? Okay, let's give it up for our speaker. Thanks.
Thank you.
Hopefully we'll see you live next year.
Thank you.